Right, let's open the slides. Can we see? Yeah. Physics, waves, stationary waves. Okay. Where did we finish? The end correction, wasn't it?
Yeah.
There's a lot here. I don't really think you need the full definition or explanation here. End correction is short distance added to the actual length of a pipe. And why do you do that? Because in pipes the antinode is formed. No. I thought you were Diego. No, it's a little bit too early for Diego, isn't it? In pipes, an antinode is formed not exactly at the open end, rather it's formed a little distance away from the open end, outside of it. There is no scientifically proven and accepted value, believe it or not. So there's no real formula for delta L. Now, how much would you need for the exam? I think the first sentence. Well, late again.
With Dr. Ryan.
Really?
Yeah.
She will corroborate this?
100%.
Oh, okay. Write down the first sentence. Just the first sentence, I think, is enough. You got that? Yeah? Hmm? Just the first sentence.
Yeah.
Okay, continue. Yeah? Yeah. So, let's have a look at, this is really simple example. I don't even think you should write it down. A boy ties a rope against the wall and stands 2 meters from the wall. He vibrates the other end so that a first harmonic is formed. What is the wavelength? So he has a rope against the wall and he vibrates it so the first harmonic is formed. Who can tell me the wavelength here?
4 meters. No?
Yeah, I think so, because how much of the wave is formed? Half a wavelength. So it'd be 4 meters here. Yeah? It's okay? I think more interesting now is the next one. This is more like an exam question. A stationary sound wave is formed in a 17 centimeter pipe which is closed at one end and open at the other. The wave formed is a first harmonic and the frequency is 500 hertz. What is the speed of sound? So this is a classic experiment. What you do is you have a pipe and you fill it up with a little bit of water, and the purpose of the water is just to change the length of the pipe. So what you discover is when the pipe is a length of 17 centimeters, and when you make a sound wave using a tuning fork, you know these tuning forks? They use them for pianos and other instruments. Have you ever seen these before?
Yeah.
So you strike it on the table and it vibrates and makes a sound at exactly, well, not exactly, but at 500 hertz. And what happens now is the pipe resonates. You get a first harmonic here. The pipe also vibrates like it was a musical instrument nearly. Okay. So this experiment, it's not very difficult to do, but this is how you calculate the speed of sound. Now, what I would want you to do is, I'll break this problem down into 3 parts. First. Number 1, you should draw the wave. Number 2, you should calculate the lambda. And finally, number 3, you can get me the V of the sound wave. Do you understand? Now I'll do it, but I'll just let you try first, see if you can do it.
So we don't have to care about the end correction or anything?
Not yet, not yet.
Can you go back to the question?
Yep, sure. Did you watch the video from yesterday?
I didn't.
I see, they all said you would, and I was kind of having my doubts.
You will find a quite nice
Wow, that's a good-
part of it.
There was a humorous part in the video, worth watching, even just for that part.
No, I'm going to watch.
Okay. I'd like you to comment when you get to the humorous part.
Okay.
Okay, will I switch back, or do you want to write the question down, Zach, is it?
No, it's fine.
Okay, will I switch back? You think you got it, Darren? Yeah. What did you get for V?
340.
That's a typical value. Got it, guys? Will we have a look at the answer? So, first, the wave, I would say, remember, it goes from node to antinode. So, I've done part 1. Part 2, the wavelength. That would be 4 times 0.17, which is 68 centimeters, is that right?
Yes.
Yeah. And then part 3. V equals lambda f. So that would be 0.68 times 500, right? And is that 340?
Yeah.
Yeah. Okay. I think I'll just do a second half with you, because I remember when I saw this question in the exam before, once they had this second half, which I thought was kind of interesting, they said there's a little valve here, and this is open so that the water comes out. And their question was, what will be the length when the second harmonic forms? I think it was, yeah. So, was that right?
So you have to calculate the rate of discharge?
No. They just want to know what would the length have to be so that I think that's what it was. I don't quite remember. What would the length have to be so you get the second harmonic?
Oh, the second.
But how do you get the second?
Yeah, so I don't know, the second harmonic, sorry, not the second, it's actually called the third harmonic, yeah. It would go node to antinode, so would that be 3/4 of a wave?
Yeah.
Yeah.
So it'd be like this.
Yeah.
So let's work out what the length would be. Let's see, so I'll make it a part 4. Find the L for the third harmonic. Okay, let me think. I can use V equals lambda F. Yes? Does the V change?
No.
No. Does the F change?
No.
So you have 340 equals lambda times 500. Now in this picture here, let me call this now L. What is the relationship between L and lambda in this new picture? Well, it would be that the length would equal 3/4 the wavelength. Isn't that right? In the picture I just drew? You know what, I'll write this as L dash to mean the new length. L dash, okay. Are you happy with that? That the new length would be 3/4 the wavelength? Yeah? Yeah. If I sub that in, I can get 340 equals 4/3 the new length times 500. Yeah. So then the new length will be 3 times 340 over 4 times 500. Okay, so what would be the new length now? .51. Okay. And what's the difference between those two numbers, 51 and 17?
0.34.
So you could say 34 centimeters of water was, water depth obviously, of water was let out. So you open it and let it drop by 34 centimeters, and then the pipe will vibrate again at the third harmonic. I don't know, you're looking 50-50 on this. What are our thoughts? Is it okay or not? Yes, no? Maybe so?
It's the same. Same wave.
Yeah,
So it
yeah.
moves. Wave actually moves. No, it's like if you took it.
Yes, do you know what? I think you're right, Diego. I think it's just the same wave, pretty much slid down until you can fit 3/4 of it in. Now, I think I probably did more work than what was needed. But the reason I did it this way is because, you know, this way works if they also change the length, and sometimes they change the frequency too.
It becomes a whole new different.
Yeah, yeah. Gina, yeah? I think
0.5.
this is 34, isn't it?
Yeah.
the difference between this and 17, yeah.
So it's actually huge.
Yeah. I suppose I'm really asking for the change in the length, but I didn't want to write that because it's not an end correction, so okay, I'll just, you know what, I'll just forget about that, it's confusing you. I'll just say the new length is 51 centimeters. Okay? Yeah? Can I continue? Yeah. Now actually there is two more examples I want to do which I don't have here. Oh, and we have two experiments we need to talk about. I'll look at the second one first. To describe an experiment to calculate the speed of sound. Well, we just did it. So, just to be clear, this is an experiment for the speed of sound. Right. Equipment. Yeah, tuning fork, let's say 500 hertz, why not, or whatever, tuning fork F, hertz. What else do we need? Meter stick. What else do we need? Yeah. What are those called?
Cylinders?
Yeah, what are they called in chemistry? The pipe. Open at the top, close at the bottom.
Oh, pipette.
Yeah.
What's it called?
Oh, pipette.
No, that's
No,
not
no,
pipette. Pipette is the small things.
Wait, you're talking about like what are they made of?
Pipette.
I don't care.
The ones
Made
that drop
anything.
that you can open
Like
and close.
glass or like
Glass is fine, yeah.
measuring cylinders?
Just measuring cylinder?
No, it's a bird. The ones that you can open and close, it's a bird. The ones for
Mine's
No,
just
they want
illustrations.
one open and one end open, one end closed.
Yeah, but at the other end you can let water
Oh,
out.
But you have the
That's
precipitation.
You don't have that?
And then you have the
Then
bird.
that is a
The
bird.
bird.
It's a barrette?
Yeah.
How do you spell barrette?
B-U-R-R-E-T-T.
B-U-R-R.
No,
One
R
R.
and R.
B-U-R.
E-T-T.
And this is you can
Yeah.
let water out. Do I need anything else? No. So, yeah. Barrette with water. Okay, fine. Okay. So, what would be the how to describe what you do?
Method.
Yeah, the methods. See, in the exam, they say describe. So you can give the method, or you can just sort of give a paragraph description. Which would you prefer? I kind of like just bullet points. Okay. Set up as shown. Bullet point 1. Bullet point 2. Strike tuning fork. 2. Slowly release water from barrette until it vibrates at fundamental.
How would you measure that?
It's really noticeable. The pipe would like start to clearly vibrate. stop, water, release, and record L. And this is the barrette. The meter stick is used to measure this, and this is the fork.
On the bread.
Oh, that's
Yeah.
volume, it's volume.
Yeah. I'm sure you could get barrettes that have lengths on them, I don't know. And then lastly, strike tuning fork F, sorry, we'll just put tuning fork F, and record L. Right, so V, the speed of sound, be equal to 4L. Why am I saying 4L?
Because it's one.
Oh, sorry. I said 4L, but I wrote
Yeah.
lambda. 4L, because in my mind, 4L is lambda. So this is lambda F. Pretty straightforward experiment for measuring the speed of sound. Yeah? Yeah, is that okay?
How would you see the pipe vibrate if it was attached to a retort stand?
You would still, you can tell. It's going to be vibrating, even if it's attached to a retort stand.
Can we do
It's
it?
going to be resonating, you know. Yeah?
Can we do it? Or
Could we? Don't have a tuning fork. Could probably buy one really cheaply on eBay though. Actually, maybe I'll look into doing that. Could use a bottle of water. You could see from the question we did, we don't need a lot. We just need 17, I think 17 centimeters was all that we needed in the height. So something like that would actually work. Although, I think the top of it is too big. It'll make too much of an error. I think a smaller diameter barrette would be better. Yeah? Now the next, can I go to the next experiment? The next experiment was, describe experiments that demonstrate stationary waves using microwaves, strings and air columns. Now, if they say describe an experiment to demonstrate stationary waves using air columns, that's actually, you could use the speed of sound experiment. The only difference is you would simply stop. Just don't do the last step. Because as soon as you do this step, you're showing that there's a stationary wave inside of it when it vibrates. Okay, do you understand? So this experiment is good for both. However, how can we change this so that we can have a microwave and a string? Well, you've seen the experiment to show you a stationary wave with a string. Remember we watched the YouTube video? Remember the YouTube video? So for that experiment you need only two things. A string and
or like the machine thing.
yeah, the little motor.
Mm.
Remember that one? So equipment. What's the two things? String and vibrating motor. And it would be nice if you can set the frequency. So I think in the video you could have a little dial so you could make it have a higher frequency or a lower frequency. And then the diagram, very simple. You have your motor, you set the frequency, and there was a little arm here that vibrates up and down, and then you have the string here, and then you hold it here, and this is the string, and the method is what? The method is quite simple. Adjust, oh well, 2 steps.
Set up as shown.
Yeah. I needed a shorthand for that. Set up as shown. Yeah, why not? I'm tired of writing. Set up as shown, and then next step is adjust F until a standing wave is formed. Even simpler experiment. Yeah. Oh, in the exam, don't write SUAS, because that's just the term we've made up now. Set up as shown. Set up as shown in the diagram. Susit.
The one with the micro.
We'll get there, man. Don't worry. Haven't forgotten about that one. It's okay. Easy peasy, huh? Yeah. Continue. Yeah. Now the last one, as Zach was preempting, is how can we show you can form a standing wave using a microwave? Yeah? Well, first things first. What do we know of that can generate microwaves? Correct. So, equipment. Microwave oven. And then, what else would we need? I would say we would want to have microwave safe beakers. Is that beakers?
Yeah.
Beakers of water, and then lastly microwave safe thermometers. I've spelled that wrong. Thermometers. Great, okay. Diagram?
So you couldn't use a mercury thermometer?
I don't know, man, I don't know. I've never put a mercury thermometer in a microwave oven.
Or if you put metal in the microwave oven.
Yes,
Like
but
bodies.
it's coated in it's covered in the glass. But will that make much of a difference?
That means it's pressurized. Or it's low.
Yeah. What about some like an alcohol or some other kind of thermometer?
That would probably work,
Yeah, not a mercury one. You're right because of the metal. Very good, very good. Yeah. Okay. Can I go down to the diagram, or well, I'll zoom out a bit. So, microwave oven with the control panel on there. And then what you can do is could place the beakers of water along it like this, and then there's the thermometers in it. So beakers of water with thermometers at room temperature. Okay. Also important to note the rotating plate is removed. You know the plate that turns?
Yeah.
That's removed. So these are not rotating.
Would that change anything?
Yes, it's important that they're not rotating.
Where are the microwaves emitted from in a microwave?
There's a panel on the left or right. So when I think about my microwave at home, it's on the right beside the control panel here. It's right here.
Yeah.
This is here the source of the microwave. Now, believe it or not, the size of the microwave oven is actually very important. You can't just make it any size. They make the size of the microwave oven so that a standing wave can be formed inside the microwave oven. So what happens is these vibrate up and down. What are these called? These are the antinodes. So what happens is, do you remember the video with the string? The same thing is happening with a microwave. There's a microwave sitting inside the oven and it's going up and down like this. And it smashes into the food, causing the particles in the food to vibrate and therefore get hot. However, what happens if your food is placed at an antinode, under an antinode? It doesn't get as hot. Where would the food get hottest? Underneath an antinode. If the food is under a node, it's not being hit. If it's underneath an antinode, what's happening? It's getting smashed with the microwave. This is why your microwave oven has a rotating plate. It's to make sure the food spends some time underneath antinodes. So by removing the rotating plate, just take it out, and lining up cups of water, you can see where the antinodes were. They would be where the hottest cups are. And you can see where the nodes were. They'd be where the coolest cups were.
Don't you need super small cups?
No, because the standing wave is actually it's a few centimetres apart. Yeah. I don't know the frequency, but we can calculate it. I can't remember, but the way I drew it, I think I'm roughly right that maybe there's like 3 or 4 antinodes in a microwave oven. So,
And would the source influence if it's higher or lower?
yeah, I think, yeah, you probably wanted at a kind of a, you probably want it in the middle. The way I drew it is actually quite bad, I'm sorry. You kind of want it in the middle so that the full oven gets covered. So I probably should have drawn that a little bit lower, maybe, so that it's more like that. But you get the idea anyways. Okay. So the method is set, what do we say? Set up as shown in the diagram. And then heat for, let's say, 1 minute. and then you note some are hotter than others. And these ones must be at antinodes, and the ones that are not must have been at nodes. Yeah. Is there a more scientific way to do it in a lab? Yeah, maybe. I'm not sure. This seems perfectly fine to me. It demonstrates that there are antinodes and nodes inside the microwave oven. So therefore, I mean, there's no other reason for this. You know,
You can do it with
if imagine you had something like this. If you can look for a second. Imagine this one was the hottest, and this one was the coldest, and this one was the second hottest, and third hottest, and fourth hottest. Then what would that tell you? It'd tell you there's a heat source here, and it spreads out. If it was like this. But if it's like this, hot, cold, hot, cold, hot, well, that can only be because there's nodes and antinodes. Logical. If it's like this, it has to be, there's a wave here of nodes and antinodes. There's no other way to get this, you know.
The waves aren't reflected in the microwave.
Yeah, it's fairly well contained, and it's a fairly well vibrating standing wave. The containment is very good for the microwave oven. The waves don't come out, they don't reflect, it's oscillating inside. Yeah? Okay, did you write that down? I have 2 more examples I need to do with you, Don. Which I didn't put in my PowerPoint, but I have them here. Oh yeah, I have a picture in my notebook here of my old workbook here. There are 1, 2, 3, 4, 5 antinodes in a standard sized microwave. So you can see that the hot points are under the antinodes.
How does the power change the wave?
It doesn't. When you turn the power down in the microwave oven, like say you set the power at 80%, what actually happens is the wave turns off 20% of the time.
Oh.
Yeah. So the power the wave is identical in both 180%. So when you set it to 50% power, what will happen is it'll turn on for 10 seconds and then off for 10 seconds. Now the next time you put the microwave on and turn the power down, you'll notice sound changes when the generator turns off. So you'll hear you'll notice that now that I've said it. And that's when it's turning on and off.
my life has been
It's
No, but what if one, say, its maximum power is 800 watts and another one is 1200 watts?
oh,
How would the waves differ then if they were both at 100%?
I think the frequency will be different. But say the 1200 watt oven, if you turn that down to a lower power, you're not making a lower frequency and making it like the other oven. You're just cutting it off every so often. Yeah. Or I don't know, Zach. Is it the frequency that's... No, I don't. Sorry, I'm sorry. I don't think the frequency is different. I think the amplitude is greater.
Yeah.
The wave goes
Yeah.
up and down more.
So it heats up more.
So I would guess if you have a more powerful microwave oven, then you're forced to have a bigger chamber. I don't think you could have a more powerful microwave oven but keep it in the same size.
Usually that's how they are.
Yeah.
It's 800.
Yeah. It has to be that way to get the stationary wave to fit inside if it has a greater amplitude. Yeah. Okay, can we go down to the next example? I want to do an example of an end correction. So the example that we did earlier, do you remember with the pipe?
Mm-hmm.
I'm going to change that a little bit now. I'm going to say the third harmonic is at 1100 hertz, and the fifth harmonic is at 1800 hertz. Now, when you last did this question, what I gave you was I gave you the first harmonic, didn't I? Which was at 500 hertz. Okay, that was enough information to calculate the V. However, if I want the V and the end correction, I need to give you two pieces of information. So you could use this, but you need to pretend you don't know the V. And you need to use this formula now. You need to, instead of using L, you need to replace that with L plus delta L. Okay? So let's do this one together. The third harmonic, how much of the wave is formed in the third harmonic? Yeah, what is it, Gina? I think you know it. Yeah, 3/4 of the wave, right? How much is formed in the fifth harmonic? 5/4. So if you were to use the first formula here, V equals lambda F, that would give you V equals, now here you're saying 3/4 the wave is equal to the length of the pipe, aren't you? Oh, but that's not true anymore, is it? Because 3/4 of the wave actually goes a little bit outside it. So it's L plus delta L. And here, you're saying 5/4 of the wave is equal to the new L, or sorry, the same L plus delta L. Yeah. We're not changing the length this time. Instead, we're changing the frequencies. So, like we were saying earlier, that's a different wave now. It's not being moved. Yeah. Okay, so here V will equal lambda, which would be 4 over 3 L, yeah, plus delta L. Now, hang on a second. I need to think about something here. F.
3L.
Yeah, I think this should be.
In brackets.
Mm,
Brackets.
Hang on, hold on. Now, let me just write. No. Yes. No. Hang on. Hang on. Yeah, maybe.
Yes.
Yeah, no. I just. Okay. Don't write just yet because I just have this sinking feeling something. Yeah, okay, just don't write just yet. V equals, and the next one would be 5 over 4 L plus delta L. F. Now, these F's are different, aren't they?
Yeah.
5 over
Oh, because we're looking at the second one.
5. 4 over 5.
Thank you.
Thanks, Mom.
4 over 5, thank you. Oh, I see you writing this down, even though you know I don't have a good feeling about this. Do I have a good feeling about this? No, I do. No, I don't. Do I? Maybe. Okay, let's see what happens. I think this will work. 4 over 3 L, which we don't know, plus delta L, which we don't know. Wait. Wait. I've not given you enough information, have I?
You did.
Did I?
Because you gave. Because.
How many equations do we have?
V must be the same, right?
Yeah, but V,
Although
L.
we have two different frequencies.
But didn't you give us L? Isn't it the same?
No, no.
17?
No, I didn't give you L. No, it's not the same. It's a different question.
Oh, okay.
Oh, yeah, I need to give you, sorry, I'm sorry. I need to give you one more piece of information because how many equations have we got here?
Two.
Two. And how many unknowns? How many things do we not know in these equations?
One,
Two.
two.
Three things. What are they?
V.
V,
L,
L, and
delta.
delta L. We know the F's.
Yeah.
So I must give you one more piece of information. I'm sorry. I'll give you... Would I give you the L?
Didn't we say that?
Why the heck not? I'll give you the L. We'll say it's the same. We'll say it's
L is this.
17 centimeters. Okay. Now let's make these equations equal. Okay. So we have 4 over 3, 0.17 plus delta L times 1100 equals 4 over 5, 0.17 plus delta L times 1800. Good, good. Okay, I guess I was worried about nothing. Can you solve this for delta L, please?
Won't be difficult. Use your graphic calculator.
Yeah.
Solve it.
Did you get it? What did you get? It should be a small number, Diego. What you got?
I don't know all this.
What you got?
So,
0.32.
That seems a bit... Now, Zach, that might be right because I just made up the L
Yeah.
of 17, which I don't even know is reasonable for this.
that is in centimeters, so we have to put them in
Yeah.
meters.
Oh, did you use centimeters?
No, no.
No, but I used meters here because I wrote 0.17, so...
Maybe 0.32.
Oh, that's 17 centimeters, so 0.1. It gives me minus 0.17 x, so which is x is delta L, and V will be 0. Which I don't really.
V is 0?
Yeah, I know.
Okay, I think I'm... You know what? I might have made up a bad number with 17 if it's not working.
Yeah, of course, V can equal 0, then it's 0 equals to 0.
Yeah, but I'm asking them for both equations, not.
Did you get an answer? Or is it a bad answer? What you get?
Shouldn't matter.
Huh?
0.32?
Yeah, okay, I'm sorry. I made a bad choice of my 17 here because this makes V 0. Which of course, it's not. Right? So, rats, okay. Well, that's what I get for making up my own number.
What number?
The problem is I used the same length as before, but you can see the frequencies are quite different. So I shouldn't really have done that. What'd you get for delta L?
Then the L was minus 0.17.
Alright.
So it's actually the same length. You just have
Oh,
to
hang on.
thing.
What did you say it was? 0.17?
minus.
Ah.
No, hang on. No, I was. Yeah. Yeah. Sorry. Look up. So you recall at this step here, I wasn't 100% confident. You remember that? And Zach encouraged me to, put the brackets in. Now, I'm not holding this against you, Zach, because that's what I thought that was right, but I forgot. At this step here, it seems like, you can say L is equal to, lambda is equal to 4 over 3 L plus 4 over 3 delta L, right? That's what we're saying here, okay? But I think the strange thing about delta L is it doesn't actually care about this. I think it should have been like this, 4 over 3 L plus delta L, and the other one is 4 over 5 L plus delta L. In other words, I don't think there should be brackets here.
Okay, so
Well, that will change things, won't it?
So delta L will be added after.
so it's everything.
Yeah, it seems like I should say the delta L, it looks like it's a constant for all waves.
False.
Yeah, well, you remember I told you that the delta L doesn't have a formula, so it's not exactly a precise thing anyways. I hope that this changes things here. So that should be now just this number multiplied by 4 over 3, and then just this one multiplied by 4 over 5.
That gives me a false answer.
A false answer.
Yeah.
A false answer.
False answer.
So if you
Let me see.
calculate doesn't work. Because it would be 4/3 times 0.17 times 1100
Yeah? Plus
Plus
1100 delta L.
plus x.
Plus 1100x. Oh, hold on there.
So 4/3 times 0.17
Plus 1100x.
plus 1
00x.
and all that times
No. Equals.
So the 110 is times delta,
Oh yeah.
just not.
And I just removed the coefficient of the fraction on the delta L, that's all.
okay, yes.
700 delta L.
Oh, big.
Big? For delta L?
No, for delta L quite small.
Yeah.
V quite big.
Yeah, well, I don't expect the V to be right because I just made up the L, but what's the delta L?
0.006476.
Yeah.
Delta L equals 0.
006476.
So 6.476 times 10 to the power negative 3.
So 6.4
times 10 to the power negative 3.
millimeters. Okay, that seems now like a sensible error correction end. Okay, I'm very sorry. This catches me out every year because it really does seem like you should have the 4/3 on the delta L, but you don't. So I guess that's a valuable lesson we all learned, and I will probably learn again next intake.
And the V was 256.
Yeah, well, it's supposed to be 340, but I just made up the L, so. Okay, is that okay? Yeah. So anyways, the point is, don't put the fraction on the delta L. The delta L is constant for the whole experiment, which doesn't quite seem right, I know, but that's just how it works. Yeah, well, like I said before, the delta L doesn't even have its own formula, so it's not even a precise thing to begin with.
If someone actually develops a formula.
Yeah, it'd actually be good going if you can.
What
But
did they even discover? Delta L?
I suppose it would be by comparing the speed of sound from another experiment, which would make you question then, you know, why is it different from this experiment, you know? That's my guess. You know, if you have 5 experiments for the speed of sound and this one is the only one that's different, then it might make you think there's some error you have to consider. Yeah. Right, I still have one more example to do. Now, is this one okay now? Yeah? Zach? Gina, it's okay? Yeah. The next one is also a little hard. Let's see. You've got a radio tower, another radio tower, and you have a car that's travelling between the radio towers at 120 kilometers per hour. And as the car is driving, it's listening to the radio. And as it's listening to the radio, it hears the signal get stronger, then it gets weaker, then it gets stronger, and then it gets weaker. So, there must be a standing wave. Wow. Beautiful. There must be a standing wave formed between the two towers. Where is the driver when the signal is at its full bars of strength? At the antinodes. And where is the driver when it's at its weakest? At the nodes. Okay, so the distance between the strongest signal is 43 seconds. So every 43 seconds the signal is at a maximum. Do you understand? Right. So the question is, what radio station is he listening to?
Oh.
Off you go.
5, 6.
Now, the name of the radio station is always the frequency. So do you remember, I think I might have said this before, if you're listening to 102 FM, I think you're listening to 102 megahertz. Let's see if you can do this and then I'll give you the answer. Are you looking up the speed of light? Because remember, because this is a radio wave,
Yeah.
its speed is the speed of light.
Oh, really?
Yeah? Why, what did you think it was?
I was trying to think how fast the wave is.
Yeah, because remember, it's an electromagnetic wave. And one property of electromagnetic waves is they all travel at the speed of light
In a vacuum.
in a vacuum.
3.8 or something.
It's 3 times 10 to the 8.
Okay.
It's actually, I think, 2.997, but
Would you say it was the speed of sound?
I think it's about 2.997 times 10 to the 8.
Is the frequency supposed to be a big number?
Yeah,
Oh, okay.
what you get?
104,651 point.
Yeah, so divide by 10 to the power of 6. Tell me how many megahertz that is.
Yeah, kind of the same. But,
Megahertz.
10 to the 6. Divide by a million. What do you get?
0.10465.
Oh, maybe I'm wrong. Maybe they don't do it in megas. Maybe they do it in kilos.
Kilos?
They
Then
do
104.
100.
Oh, good. Sorry. It's kilohertz. The FMs are in kilohertz.
104.65.
Yeah, so that's
So
he's listening to 104.6 FM.
0.6, no, 0.7. 0.7.
Is it 0.7?
Yeah, if you round it off, yes.
Well, I got
But
point.
do they go
45.
to 6.5 or to digitals at the back, or?
I think for FM radio stations it's 1 decimal point.
Okay.
So, how do we do this? First thing you have to get is the distance between the peaks.
Quite big.
Yeah, well, it'll be 43 times. Now you have to convert this into meters per second.
33.3333.
Thank you. That was this number over this number. Yeah. Now, do you remember we said twice the distance is the wavelength? So this multiplied by 2 is the wavelength. And remember, we have V equals lambda F. So F equals V over lambda. So the frequency will be 43 times 1200, how many O's? 4 O's, isn't it? Over 3600. What was I writing here? Times 2, sorry. Times 2. And then that's over. No, that's the wavelength, isn't it? So that's under 3 times 10 to the 8. And you said this is 101 point. No,
104.65.
So to 1 decimal point
104.7.
kilohertz. So that means he is listening to 104.7 FM is the radio station he's listening to. Because like I said, kilohertz is what radio station frequencies are measured in. Yeah? Would you know any radio stations here? No? Back home?
Back home, that one exactly.
104.7. 104.7 is the one you listen to back home.
Yeah.
Wow, isn't that amazing?
It's called Fun Radio.
Alright, so we can say, we can note 2 things. We're driving in Spain.
No.
No. Where?
Belgium.
Okay, we're driving in Belgium. And the name of the station is
Fun Radio.
Fun radio?
FUN and then radio.
and then what?
Radio.
Fun radio. Nice.
radio station.
So we're in Belgium, driving along, listening to fun radio.
Watering physics and trying to understand.
That's it.
104.7.
Nice, very nice. Okay, so I saw this. Okay, well, obviously, when I saw this in the exam, they didn't ask you what radio station you were listening to. They asked what was the frequency of the radio station. Yeah. So the standing waves, the hardest question is the end correction. Now, the good news is 90% of the time there's no end correction. The end correction, they only put it in 10% of the time. So this is why I sometimes forget how it works, because it doesn't actually come up that much. Most of the time it's just, here is a length, here is a tuning fork, what is the speed of sound? Or the speed of sound is this, and the length is this, what's the frequency? Or something like this, so it's not that difficult. Right, well, there's plenty of time left. You should get all the questions finished on this, and then next week we'll begin looking at the experiments then. We should, Diego, we should like tag this on YouTube.
Yeah, it's kind of like electronic dance music.
You can tell them that they are famous now. They're in Stephen's physics class. They're listening.
Send them
the video, yeah, the YouTube, yeah. You now have six more listeners. Right, okay. Can I close this? Yeah. I can close this?
Oh.
How many are there?
No, I scrolled past it. I just saw something. That was,